I want to start off this video by doing a short review of the project and just make sure that everyone remembers and recognizes all the key components and the requirements and everything that have been laid out in the documents posted previously on Blackboard. You will do these projects individually. They're not group projects. Your projects must be a complex GIS analysis of your choosing. In other words, I don't want some simple thing like where are all the whatevers located. That's not what this is about. This is about a complex analysis. You have to write a brief formal project proposal, and I have to approve it because I don't want you to spend a whole lot of time working on something that's not going to work. Your final project will consist of a report that has multiple required components. It has to be written to a required length and in a specific style or format. And once it's done, each student will develop a short PowerPoint presentation of the project to present to an end user. Now, for most students, this will be in class. If you have difficulty presenting in front of large crowds or any other issue that would make you more comfortable presenting this in a more personal environment, I will allow you to do your presentation to me in my office. But I need to know ahead of time that that's what you're going to do, and we have to work out when you're going to do that, and it will have to be done prior to the in-class presentations. If you haven't made arrangements by that point in time, the expectation is you'll do it in class. If you don't do it in class and you haven't made those arrangements, then you will not fulfill that requirement, and you will ineffectively be in violation of what we require as a minimally acceptable effort, and you will fail the class regardless of what other grades you have. Everybody will submit your proposal, your report, your map package, and the presentation for grading. If you don't produce the final products at these acceptable levels, you get a score of 0. If you fail to complete the project or several components of the project, it won't be accepted and you get an F in the class regardless of whatever else scores you have. So you don't do the project, or you don't do certain parts of the project like submitting your map package or doing your presentation, you're going to automatically get an F. So what are the general rules for the proposal? Word document or the equivalent of that shouldn't exceed 1 page double spaced in 10 or 12 point font with 1-inch margins. I expect you to use good grammar and use GIS terminology correctly. Your proposal has to include the following sections: the author, the course information, your GIS question, background information, general methodology, preliminary list of data sources, and expected maps, tables, and or graphs to be produced. Now what that means is, imagine a single page, and it's going to start off with who you are, what class this is, and then the next line will be what your question is. Now I'm going to be a bit of a stickler on this. If you don't have an actual question on this, I'm going to give it back to you or grade it as incomplete or a 0 or whatever, because basically if it's not a question, how can it be a GIS question? Don't tell me what you want to do. Oh, I want to do this. I want to look at that. I was wondering about. No. I want a specific question. What's the best location to build this cabin? How much land will be flooded by the creation of this lake or building this dam? Those kind of things are specific questions. I want to look at how the demographics changed around a certain community after something was built. That's not a specific question. Don't write something like that. Background information is just a couple of sentences or so telling me why your question is important. General methodology explains in the most broad sense how you're going to answer that question. Preliminary data, what data you're going to use to answer it, and then what sort of maps and tables and or graphs you expect to produce. That will help you explain your answers. Your draft submission. Complete your proposal, place it in your homework folder by Monday, and I'll grade it and provide feedback to you by the next class. If you place it in your homework folder by the next class, I'll grade it and provide feedback by the following Monday. For final proposals were due in week 11, but I have extended that to week 12 because of my illness and not being able to be at class tonight. General rules for your final project: 5 to 8 text pages, double-spaced, 12-point font, 1-inch margins. Don't try to put in extra spaces between paragraphs and crap like that. It just doesn't count. 5 to 8 means this: it has to be 5. It shouldn't be more than 8. If it's not 5, it's not completed at the required level and will be an automatic F in the class. If you produce a final project, that paper that's more than 8 pages, after 8 pages I'm simply going to stop grading. It will count as a completed project, but your grade will suffer because anything that was required that's beyond the 8 text pages, I simply will give you scores of zeros on. So what is a text page? This does not include your maps, your charts, your graphs, your references, or your cover page. It's everything else. Don't stick your maps, your charts, and your graphs in the text. They belong at the end of the document. It should look like this. It starts off with a cover page. Then you go right into your text stuff. Different components that you have to write about, executive summaries, methods, etc. Once you get through all those sections, next thing that should come will be your references, where you talk about all the data that you have. And remember, if you used a source of information, you should mention it in the text and then include that reference in the reference section. Following the reference section, you'll have your maps, your charts, and your graphs. Identify them as like figure 1, figure 2 for maps, table 1, table 2 for charts, figure 1 or figure 2, etc. like that for graphs. And every map, every chart, every graph in your report needs to be referenced in the text. If it doesn't say in the text somewhere, you're talking about a particular map and you say see map 1 or see figure 1, and that takes me to the map of what you're talking about. That's how it's supposed to set up and work. If you put in maps, charts, and tables and don't reference them in the text, they don't count because they weren't necessary because you didn't even talk about them. If you talk about a map or a chart or a graph, you need to make sure you include it. Cover page should have the name of your study, your name, and the name of this class, and that's about it. Number each page at the bottom, beginning on the first text page. Do not number the cover page. If you're not sure how to do that, come see me sometime before the end of the semester, and I will show you how to do that. General rules: spelling and grammar are important. Use GIS terminology. Cite your sources, including the data that you use, by the triple essay citation style. This link will take you to a quick guide to this style. There's nothing magical about this style. What is magical is the fact that there's about 10,000 different styles, and you need to learn to write references relative to whatever style you're required to use. So getting to know another one's not going to hurt you. General rules for the final project: every report must contain these mandatory topics or headings. In other words, you have to have these sections. Now, cover page does not need to be labeled cover page, but you need to have a cover page. We already talked about what belongs in a cover page. You should also have an executive summary, and you should have an introduction and a method section, results and conclusions, your references, and then your charts and tables. Now, what are these things? The executive summary should explain in totality what the project is about. It should start off by listing your question, explaining why it's important, telling me how you solved it, what data you used, and what results you come up with, and what conclusions you drew from that analysis. And it should do all that in a paragraph or so. It should be brief, but it should allow me to read that and get a complete idea of what your report is about. The introductions, where you're going to go into some detail about the study area, specifics of what you're doing and why it's important, what you're trying to figure out, those kind of things. Your method section is basically how you did things. It should always start out by stating your GIS question, and then following that question, explain how and what methods you used to answer it. Results and conclusions are the output or the solutions you rendered from your analysis and what they mean. This is where you should be referencing your tables and charts and graphs and figures and whatnot at the end of your paper. When you're talking about results, you should reference those tables and figures that relate to those. References, you should reference every bit of information that you use to create your reports, charts and tables, like we said before. The final report is your chance to provide a decision-maker quality, unbiased information as a key element of the decision-making process. So here are some of the things that you have to do. The final project is an exercise in advanced GIS modeling. Simple stuff like where's the this and where's the that does not count as advanced. You need to be able to combine multiple data layers using various geoprocessing techniques to create data that is not easily created, or to answer questions that are not easily solved outside of a GIS. The project you choose has to have certain steps and or criteria. Every project has to use Model Builder. Every project should use a minimum of 3 separate datasets for analysis or display. All projects are required to utilize at least 2 geoprocessing procedures. All projects are required to address a question that cannot be answered without the use of GIS. All project reports must contain a minimum of 2 maps and 2 figures, that can be charts or tables. And data used in your project should be publicly available. Now I'm going to go back over this a little bit just to make sure we're clear. Once you figure out how you're going to solve your question, you need to set up those steps to solve that in Model Builder. You need to have at least 3 separate inputs in that Model Builder. That's where your 3 datasets come from. You are required to utilize a minimum of 2 geoprocessing procedures. This does not mean 2 different ones. This means at least 2 geoprocessing steps have to occur in the Model Builder. All projects are required to address a question that cannot be easily answered without the use of a GIS. We've talked enough about that. I think that's pretty clear. And I want 2 maps and then 2 charts or 2 tables in your projects. The data used in your project should be publicly available. Doesn't mean it has to be, but if you use data that's not publicly available, you need to make sure that it's okay to use it. Just a little FYI. To be considered a completed project, the maps and figures you produce should support the analysis that you're doing. If a map or table is not useful or discussed in the report specifically, then it doesn't count. I don't want you to make maps and tables and charts just for the hell of it. We don't make them just to make them. If you make them, you should talk about them in your results and conclusions, and they should be meaningful in terms of your analysis. If they're not, then they don't count. Your project will be considered incomplete if you fail to produce the following. And when I say incomplete, I mean, and let me be clear about this, it means if you don't do all these things, you will basically fail the class. Okay? Your project must have each required component. If I say it has to have X, Y, and Z, it has to have X, Y, and Z. You have to submit a final proposal. Even if it's 3 weeks late, I need to have that at the end of the semester when you submit your project. You won't get any of the points that you get for it, but it has to be submitted in order to pass. You have to have at least one useful map. If you don't make a single map that's useful in terms of explaining your analysis, then you're not progressing as a GIS analyst, and you should fail the class. I told you need to have 3 data sets or data layers. That's what you're required to have. If you don't have at least 2, I don't know how you're going to do a complex analysis, and so you will in effect fail the class. If you only do a single geoprocessing step, I'll accept it. There'll be penalties for that, but it will be considered meeting the minimum requirements. If you don't have any geoprocessing procedures, you're going to fail the class. So here are what the parts are. I'm going to talk a little bit about specifically what they are. Cover page should basically just have your name, the name of your report, the name of the class, basic stuff. Executive summary, like I said earlier, it's a paragraph that explains what the question is, why it's important, how you plan to solve it, how you planned to solve it, or what you did, how you did it, what you discovered. It should be a brief summary of the entire report. It should be the last thing you write. I should be able to read that and have at least a basic understanding of your entire project. What you did, why it's important, how you did it, what you found out. Your introduction is where you make the case for why this is important, and you provide any necessary background information so that we can understand why it's important. Your method section is basically how you planned or what you did to solve your GIS problem. The results and conclusions are what you found and what that means. References are what data you used. Your charts and tables, and I guess I could include maps there, are the things that you generated that explain or are explained in your results and conclusions. Your map package. You create a map package so that you can send me your entire GIS project in a single, compact, easily transferable file format called a map package. Don't send me a layer package. Don't send me a geodatabase full of stuff. Don't send me a map file or an ArcGIS map document. I want a map package. Now, we've talked about that earlier in the semester as to what one is. When we get near the end of the semester, I will in class go over how to create one. Again, if you don't understand what a map package is or how to make one, you need to talk to me, because if you do not submit a proper map package, you will fail the class. Lastly, you have to create a PowerPoint presentation on your project that you're going to present either to me or to the class. And if you don't know how or are not familiar using PowerPoint, we will cover the basics so that you can create a presentation that will be adequate for these purposes. The second part of what we're going to talk about today is modeling, and we're basically just going to review what we covered earlier this year and provide you a video, a little typo there, reference to help you with your project. So when you're trying to think about, how you want to set things up, you can go back and maybe listen to these sections again, and it'll make more sense, and you'll understand what you need to do. We're going to talk a little bit about the modeling process, because this is what you should be going through now as you develop your proposal. First thing you need to do is define the goals of your model. In other words, what is your question, and figure out what kind of answer you need to get. You have a question and you need to know what answers you get, because that's going to dictate the steps that you need to take to get there. You're going to break down your model into elements, define the properties of each, set up interactions, maybe set up a flow chart. I like to sketch it out on paper. What's my problem? Okay, what are my inputs going to be? How am I going to combine those inputs, and what steps or processes do I need to do? And what kind of output am I going to get from each of those, and how do those outputs lead to understanding or developing an answer to the question? When we talk about complex models, oftentimes we're talking about things that are not very necessarily local in scale or very specific. They tend to be bigger things, to where we might have the ability to tweak the model. So we run it through and we figure out what's what, we adjust it, maybe we change some of our weighting variables or how we set up some things. We can do sensitivity analysis to see if one or more of our variables is really driving the model, and maybe we need to address that. And ultimately with this, we can then calibrate it to the real world by validating it, which is the next step. In other words, we can take real world conditions and apply it to our model and see what happens. Now, for a model to really truly be valid, you have to create it, and then you have to run it, and then you have to compare it to other data to see if it's going to fit. Now, we're not going to do that in this class for the purpose of this class project, but the same process still applies. You figure out what your model is, you run it, you adjust it, tweak it, change your weights and things like that until you're happy with its output, and then you use your model to answer your question. We're going to talk about 4 basic types of models. First is the binary model. This uses logical expressions to select spatial features from a composite feature, vector layer, or multiple rasters. The outputs are Boolean in nature, 1 being true, 0 being false. It's a pass-fail, it's a yes-no, it's a is or is not kind of a thing. Complex analysis do not necessarily lend themselves to purely binary models, in my opinion. A basic suitability model of where are the possible locations for X, where you have multiple data layers and you say these are the criteria we must meet between these different layers, and you can identify the layers, the locations within each layer that meet the criteria, and then figure out what locations are common to all 3 sets, and that works. But it really limits your options, and it doesn't give you a way of selecting one location over another. So it is common to use in siting, but it really only identifies all the possible locations. It doesn't really help you find the best. Next, we're going to talk about an index model. An index model calculates index value. An index value produces a ranked map based on the index values. But remember, an index value doesn't really mean anything. They're similar to a binary model. They both involve multiple criteria. They have some overlay operations for data processing. But an index model produces an index value rather than a simple 1 or 0. So what is an index value? It's just a number. It doesn't mean anything. Index value of 12 means it's better than an 11 but not as good as a 13. It's just that simple. It is a ranked evaluation where a particular score has meaning only in the context of the other location's scores. Weighted linear combination method is a pretty straightforward way of calculating an index model. It involves evaluation at 3 separate levels. You have to figure out what's the relative importance of each criteria or factor relative to each other. In other words, you got 3 variables, which one's the most important, the next most important, and the least important. The data for the criteria have to be standardized, because if you don't, it can create a lot of problems. Unstandardized data means that certain variables can dramatically change model outputs and effectively mask changes in other variables. Then you calculate your index value for each unit area by summing the weighted criteria value and dividing by the sum of the total of the weights. So here's an idea of how to build an index model. Pretty straightforward. We have these 3 different data layers: slope, aspect, and elevation. This is a pretty good example of how you would build an index model for, say, a cabin location. So we have maps of slope, we have maps of aspect, and we have maps of elevation. And we assign a weight as to which one we think is the most important of the 3, the second most important of the 3, and the least most important of the 3. We standardize our values because slope is in percent, aspect is in degree, and elevation is in feet. You can't add those together and get a meaningful answer. But if you use something like, I don't know, maybe standardization that would make all the values between 0 and 1, or between 1 and 100, that could be very helpful. You could create them all in the z-score so that the values were we looked at them in terms of how far they are away from their means. So there's lots of ways you can do it. Anyway, once you standardize the data, you use some processing to combine those in some meaningful way, map algebra or something of that sort, to aggregate your data into your final output. So what are the sticking points? Index values, standardized values, weighted values. To get an indexed value, you need to standardize and weight everything and then combine it. Remember, index values are meaningless. They only indicate a degree of fit, suitability, or success. In and of themselves, they mean nothing. They are only used for comparative purposes within the individual model. Why do you standardize? Because scale measurement can overwhelm the output. Why do we weight? Because some things are more important than others, and some things we include in the model, but we just know that they shouldn't be as important. How do we standardize? 0 to 1 scaling, dividing by the range, z-scores, dividing by the standard deviation. These are all appropriate techniques. I'm going to fly through them very quickly because I've already given you the document on doing this. Here's an example data set. You have 10 data points, values of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If you take that data set, calculate a mean, 5.5, standard deviation, 2.87. You use 0 to 1 scaling. You take a particular value minus the minimum value, and you divide that by the maximum value minus the minimum value. And it gives you this new output. That looks like this. What was once your lowest value is now a 0. What was once your highest value is now a 1, and everything else is somewhere in between. Point of note, if you're going to be working in a raster data set, this is not the best technique to use because raster attribute tables do not like to deal with decimals. But if you were to take this data set and multiply it by 10 or by 100, you can have a 0 to 10 or a 0 to 100 scale, and that would work much better. And you can also divide by the range. In other words, you take a given value and you divide it by the maximum minus the minimum, and that will give you an output that looks somewhat like this. And you can see that when you do that, your values are slightly different, but you'd have the same problems with certain raster attribute tables. Z-scores, a value minus the average value divided by the standard deviation. Gives your answer in terms of how many standard deviations you are away from the mean. And you'll get numbers like this. In this example, you see that your lowest score is negative 1.6 standard deviations away from the mean. Your highest one is positive 1.6. Again, could create problems in some data formats to deal with these negatives and decimals. You can also take a value and simply divide by the standard deviation. Now we're going to look at how you can apply some of this stuff. This is a vector-based index model where you have these two data layers. Use a map overlay function, and when you do this, the primary difference between this and a spatial join is it allows you to intersect features, and so things don't have to line up perfectly. It artificially creates a one-to-one cardinality so that every space in the data set has all the appropriate data. We don't have to do any averages or sums or any kind of summarized stuff. And so when you do that, you, in this case, combine data set 1 and data set 2. You get this overlay output where you have these new polygons, and you have data set 1 and data set 2 for that. You can then standardize those variables, and then you can combine them or weight them or do whatever you need to generate your final outputs. And they're talking about standardizing those before you combine them, and I guess that is the proper way to do it. And ultimately you calculate your index value for each polygon in the output by summing the weighted criteria values. And here is an example of how you could do that. In a raster-based scenario, it is also very similar. You have 3 input rasters. You can standardize these. This example uses the 0 to 1 scale. We then apply a weight to each one, 0.6, 0.2, and 0.2, weights that reach a sum total of 1 in this example. Multiply the weight by the standard values, and then combine those weighted standardized values into an index. And that's what you get. And that's pretty much the way this thing works. Any given value is equal to an individual property multiplied by its weight. How do we use index models? Commonly used for suitability analysis and vulnerability analysis. I'm going to talk just a little bit about regression models. They relate a dependent variable to a number of independent explanatory variables into an equation that can be used to predict or estimate something. You can use overlay operations in GS to combine variables to make your analysis complete. If you know that certain combinations of things lead to certain other things, because you've done a regression and you're comfortable with the output that certain combinations of variables will give you what you're looking for. You can simply do that in GIS. Talk about two types of regression models: linear, all variables are numeric. You need to read up on what are some of the assumptions with linear regression to fully understand it, and if you don't, you probably should stay away from regression modeling. And then there's logistic regression, where you can have categorical data as well. Last, we're going to talk about a process model. Process models integrate existing knowledge about the environmental processes in the real world into a set of relationships and equations. It quantifies the process. Environmental models are typical process models. They must deal with the interactions of many variables, including physical variables such as climate, topography, vegetation, and soils, as well as cultural things such as land management. Now, these models are not always cut and dry, falling neatly into one category. In fact, it's not uncommon to construct a model where you have some data layers that you have a Boolean sort of feel to it. Like if you're looking to build a cabin on a certain stretch of mountainous terrain, you know for a fact you can't build on national forest. So you might have a layer that says where can I and can I not build. And so you would classify the land ownership as publicly available or national forest. And in a scenario like that, 1 would be a 1. That's the available stuff that you could buy. The other layer would be a 0. And you would use this to eliminate any possible locations that there's no way you could purchase. You could combine that with a relatively complex index model dealing with like slope and aspect and elevation to find a high perch with the right facing slope, with the right facing aspect to utilize something like solar power, and to be positioned such that the slope won't be a problem for building. And so you could calculate up weights for those, because what's really important is that you're above a certain elevation because you want to be high on the mountain, and you want an aspect that faces in a certain direction so that you can utilize solar power. And so you weight both of those maybe at 0.4, and then you assign a weight of say 0.2 to the slope, because the amount of excavating that you have to do is important, but it's not as important as those other factors. You could also use fuzzy membership functions to work around some of these things, and I'll talk more about those in a minute. So I want to talk a little bit about creating suitability layers. Just remember, before you combine layers, they have to be standardized, or not, depending. If you rank your variables, then you should standardize them, or you are standardizing them. If you weight your variables, in a sense, you are standardizing them. If you use multiple forms of standardization, you are somewhat weighing model terms, but it's not a very good technique. In other words, you don't want to use different standardizations like 0 to 1 or z-scores together, because it defeats the purpose of standardizing if you don't use the same standard. You want to stick to a single scale when you're doing things. In other words, if you're categorizing things, sets of 3s and 9s are commonly used. Exclusion is your friend when you're creating these layers. Don't be afraid to use Boolean layers as an exclusionary layer to eliminate some locations. You can use this to run virtual what-if scenarios and create alternative scenarios, evaluate your model, your weights, and everything. It's very similar to sensitivity analysis, but it allows you to look at other options. There are also a lot of options for how you can combine your weights in layers. For example, you can add your layers together, or you can multiply them, or maybe you add some and subtract some, or you multiply by some. You have to make a decision for how these pieces fit together. Okay? If you know that distance from a stream is important in a good way, then all you have to do is use a fuzzy membership function or an indexed value for that field that gives you higher points for being closer to the stream. How could you do something like that? Well, you've got a distance. I'm 1 meter from the stream, I'm 10 meters from the stream, I'm 100 meters from the stream. If you simply divide 1 by the distance from the stream, you get a numerical value. Okay? You then simply standardize that using your standardization techniques that you use everywhere else. And now this function will give you more points the closer you are to the stream, less points the further away you are, and it would do that with this basic value of 0 being the furthest possible place away from a stream and 1 being right at the edge of the stream. Now, if being close to a stream was a problem, then you could simply take the distance from a stream and standardize it so that the distance was converted on a 0 to 1 scale, so that 1 would be the furthest away and 0 would be the closest, and they would all be between 1 and 0. Straightforward. The trick is you have to figure out whether something is a good or a bad thing. Is it something that should contribute or add to a score or take away from a score? Now, ultimately, you don't want to necessarily go in and start subtracting things in a model. You want to create a data layer. Well, it's best to create a data layer that adds to the model. And so you want to do things like convert the score, like I mentioned earlier, where you divide 1 by the distance instead of subtracting your distance value. Anyway, that's what you could do. There are lots of ways you can do this, and you can discuss it in a lot of detail if you wanted to try to figure out how to come up with some of these things. Fuzzy overlays rate locations continuously based on many layers or inputs, all which need not be fuzzy. It's based on logic. Fuzzy membership functions are really neat because on a given data set, you can, for example, if we looked at elevation, you could create a fuzzy membership function that if you said you wanted to build a cabin that was above 3,000 feet, you could give everything below 3,000 feet a value of 0, and then everything from 3,000 feet to the maximum elevation in your data set increasing importance that you would then standardize between, say, 0 and 1, so that you would have a whole bunch of zeros up to 3,000 feet, and then incrementally increasing that value until you reach the highest elevation that would have a value of 1. In as many ways as you can consider things like this, you can create these functions. If you're looking at, say, aspect for where you want to put up a solar panel, or if you're looking at it for that context and you want a south-facing slope, you could say that directly south is perfect score, and that everything south, southeast, and south, southwest would also be perfect, but anything east southeast or west southwest would not be. And so you could literally set those degrees. In other words, south being 180 degrees, you could say it at everything from, say, 50 to 210 or something like that, would all be a value of 1. And then you could pick another 10 or 15 degrees on either side and calculate a fuzzy membership function for that. That would give you a value of decreasing acceptance from 1 to 0 out to whatever that threshold of degrees is on either side of your perfect score, to where it's no longer considered useful. So that you would have, if you started at 0, which is north, and begin moving south, you would have a value of nothing until you got relatively close to south, and then it would start increasing until it got to 30 degrees or so from being due south, and then it would be a perfect score until you were about 30 degrees past due south, and then it would decline for a little bit until it got back to 0, all the way back up till it was facing north again. Now, we generally create and work on fuzzy membership functions and that kind of stuff in our 3D class, because it's a type of modeling that tends to be more useful in more advanced stuff. But we're going to mention it here in this class, and when I come back in class next week, I'll sketch out what some of these things look like, and we'll talk about this again before the semester's over. And if anybody thinks you might be interested in using one of these in your project, I'd be happy to sit down with you and talk in some detail about what you can create with these.